Okay, so we're back here continuing to talk about pressure and fluid statics. And in the last video, we talked about Pascal's law, and we said that that tells us that the pressure at any 2 points in the fluid is the same. And that allows us to use hydraulic machines. Here in this video, we're going to talk about manometers. So manometers are devices that measure pressure. Okay, so this is a chapter's about fluid statics and pressure, and manometers kind of get at both of those. So the devices we use to measure pressure. In actuality, the manometers measure pressure differences. So they don't measure the pressure, they measure the differences in pressure between points. Okay. Generally, there are two kinds of manometers. They're really, you could argue that there's only one kind, but there's two general classifications, and those are going to be differential, meaning they measure differences in pressure at two different points in a system, and then open, meaning that they measure the gauge pressure. Okay, so this first example here shows how we have like a pipe. You can imagine this is a pipe that's running out of the page, and it has a pressure, and because it has a pressure, it's going to push here on the fluid. And we have a second fluid here that is used in the manometer. This second fluid is going to be a lot heavier, and so this pushes down there, and it kind of raises the level up. We know from Pascal's law that at point 1 and point 2 the pressure has to be equal. Okay, so over on the right side here we have the atmosphere pushing down on this, and then we have this little bit of height here. So this height of fluid pushes down on this point 2. The atmosphere pushes, and then this weight of this bit of fluid pushes down more, and then that has to be equal to the pressure here that is transmitted from the pipe down. So the pressure here minus whatever pressure drop there is associated with this little height there. Okay, so we can use a force balance then to figure out what the pressure is here in the pipe if we know the weight of the fluids that we are looking at. So this is the open manometer here, and then on the right here we have a differential manometer, and so this shows like a pipeline where we have one. You can imagine the pipe kind of runs out of the page and curves and goes through these 2 points. And if we want to know how much the pressure changes between these 2 points in the fluid, we can then look at this manometer here, where again it's a separate immiscible fluid. Immiscible meaning that it doesn't mix, so like water and oil, for example. But oil wouldn't be a good choice because it's light. It would need to be something that's much heavier than water if we were using it here. So again, if the pressure is higher here at point A, it will push down on this heavier fluid and cause it to be higher on the right than on the left. At point B, you have another pressure here that's pushing down, but so pressure at B would be lower. And the difference we could figure out from a force balance here. So this is the differential manometer. Okay, and so let's do an example where we analyze one of these manometers. And so here we've got a gauge and a manometer, and so we have a gas tank over here on the left, and it's got a gauge pressure of 65 kilopascals. So PG stands for gauge, and so that's pushing here. And then we have an open manometer, so there's an immiscible fluid here on this side that's heavier, and so again we have this piece of fluid there that is pushing. The weight of it is pushing down, and it has to be balanced by the pressure of the gas pushing from this side. Okay, so if the reading on the pressure gauge here is 65 kilopascals, we're supposed to determine the distance that this will rise for 2 different scenarios. One of them is if this fluid is mercury with a specific gravity of 13.6, and the other one is if it's water with the specific gravity of 1. So here we have PG, the gauge pressure is 65 kilopascals, and then again we've got the atmosphere pushing down. The atmosphere pushes on everything, so it's pushing on the surface of that, and then we have this height of water here, so we know the pressure is the same at these 2 points. All right, so the force here, we have the atmosphere pushing down, and then we have the weight of this part of the fluid and that's going to cause a pressure change here. So we're starting at atmospheric pressure, and then it's going to increase linearly as we drop to an amount h times the specific weight of this fluid at that point. So it'll be P atmosphere plus gamma for this fluid times H will be the pressure there. And on the right side we have the gas, and if you have a gas, we can think of the weight there as being basically negligible. So this height change in the gas, the pressure up here and down here in a gas is going to be effectively the same. If you go up and down a building, you don't feel a significant change in air pressure. You have to go up a long ways for that to be significant, okay, because air is very light. Now that's not true in something like water if you go down in a swimming pool or lake, okay. So this is an important rule to remember, is that for gases, going up and down doesn't really change the pressure significantly, but in liquids it does. So basically, because it's a gas, that makes this a little bit easier. So we can assume the pressure here is the same as the pressure there. So, P, or say pressure is the same, there and there, because it's a gas. So don't forget this. This is a mistake I see all the time from students with gas. Okay, because it's a gas. All right, but so anyway, basically we have, if we do a force balance here across these points, then we know the pressure is the same. So that means that P atmosphere plus gamma for this fluid times H needs to be equal to P gauge over here. And remember that if we look at the absolute pressure here, we have to add in the atmospheric pressure. So balance, so a force balance would tell us, force balance is going to tell us that the pressure at this point and this point are the same. P at 1 is equal to the P at 2, and then the P at 1 has to be equal to the total pressure at that point is going to be Pg plus P atmosphere, and that then needs to be equal to P atmosphere plus the weight of the fluid on this side, and the weight of the pressure from the weight of the fluid is gamma times H. Okay, and so we have P atmosphere on both sides, and so that's the reason we use these open manometers, is because it's easy, relatively easy. We just have to be able to measure this height, and you can see that Pg, the gauge pressure, is equal to gamma H for an open manometer. And so we have, for part A, we're looking at mercury. In both cases, we're going to need the specific weight of water. Here we're working in metric units, and so the specific weight of water is 9810 newtons per cubic meter. Okay, so remember the density of water is 1,000 kilograms per cubic meter. If you multiply that by G, you get 9810 newtons per cubic meter. And so it's just handy to use this. You can use rho and G, but it's just more work. So why not just use gamma? Get used to doing it this way. All right. And so for part A, we have gamma for the fluid is equal to 13.6 times gamma water. And so then so we have Pg here is equal to gamma H, and that means that H is equal to Pg over gamma. Pg over gamma. Okay, and so H here then is just going to be the pressure, which is 65 kilopascals, and that is divided by gamma, which we said is 13.6 times gamma water, which is 9810 newtons per cubic meter. And since it's in the bottom, the meters cubed goes up to the top, and so then we need to do the unit conversions here. And so a kilopascal, remember a pascal is a newton per square meter, and so that means that 1,000 newtons per square meter is equal to 1 kilopascal. So this is just multiplying by 1, and that gives us then units of meters here for the height, and we get 0.49 meters that it will rise if this fluid is mercury. Okay. So this is for part A, and then for part B we have gamma is equal to 9810 newtons per cubic meter, and it's the same calculation. So H is equal to 65 kilopascals, and then divided by, instead of 13.6 there, it's just the 9810 newtons per cubic meter, and then times 1,000 newtons per square meter kilopascal, and we know that the units on that work out, and that gives us 6.62 meters. Okay, so you can see if you use mercury, then this is only going to rise up by about a half of a meter, whereas if you use water, it's going to rise by 6 meters. So you would need a really long tube if you use water. So that's why this is often done with a heavy fluid, so that you don't have a huge change in height that happens there. Okay, so we'll pick up there in the next video.